And we are ready. Okay. Hello, everyone. Welcome to a new episode of our Machine Learning Security Seminar Series. I am Maura Pintor, and I'm an assistant professor at the University of Cagliari. Today we have a guest from INRIA, Yufei Han. But before we start, I would like to share a few things before. First, the event is live streamed and recorded, and you will find the recording after the seminar on the YouTube channel that we have, and we share in our website. Also, if you would like to know more about machine learning security, in the same YouTube channel, we have all the past events and also a free course on machine learning security available on a separate playlist. Then I would like to thank all the people who helped me organize this seminar series. And now I will leave the stage to Luca to introduce the speaker for today.
Yes. So thank you, Maura. So Yufei Han is currently a senior researcher at INRIA Pirat project team, and he's focusing mainly on two topics. One is adversarial attacks and defenses on AI techniques, and AI-boosted cybersecurity applications such as AI-based malware detection. Yufei has over 30 peer-reviewed research publications on top venues and journals of AI and security, such as ICML, iClear, AAAI, KDD, ACM, CCS, and SMP in Oakland, Usenix, and TDS, the TDSC journal. And also, it has also 15 US patents granted. So this man is really delivering a lot of content. So thank you again for being here. The stage is now all yours.
Thanks, Luca. Thanks, Moha. Thanks for providing me this stage to share my recent work. So let me just share my screen. Okay, so this is the slides. Did you guys see the slides now? Okay.
Yes.
Putting
but we can go full screen.
Exactly.
Okay, great. Let's go.
This is what we have. Okay, so thanks again for inviting me to share my recent progress here. So the work I like to share with you guys today is the cross-context backdoor attacks against graph prompt learning. And this is one of the publications that we got accepted recently by KDD 2024. And it's joint work between INRIA, which is me, and the other guys from CNRS in France and A-Star Institute in Singapore and University Notre Dame in the US. So before we really dive into that topic, I want to bring some context information. So some of you may know, or the other guys may not know, it's like what is graph machine learning, right? So usually we receive feature vectors and we put into a machine learning model such as like deep neural networks and support vector machine, blah, 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 and we get prediction output. So this is the Euro baseline pipeline that we have. But graph is different from the tabular data we usually have. We don't have a feature vector to present such a graph, because graph, you basically have two kinds of resources. Like first, you have the features for each node. And second, you will have the structure information between the nodes. That the topological stuff can also tell us the story about a graph. For example, like a social network. You not only know what is the preference of each user, but also you will be interested with what is the relation between different users. They tend to share similar preference or not. So these kind of things will be encoded in the graph structure data. And another example is like the biomedical data. So like we want to categorize the molecule structures, and the structure means a lot in that case. So graph machine learning is to take a graph as input and compress graph into let's say, embedding vectors that can be used for the downstream tasks. Like, for example, you want to classify the nodes, like categorize the users on social network, or you want to do a graph classification. You want to categorize, for example, the molecules, or you want to do visualization. So you want to say, okay, if you have different molecules, can we do the clustering of the molecules and put into some 2D space and visualize what's the group of these molecules. These are the definition for the graph machine learning. And talking about the backdoor attack, and usually when we talk about the cybersecurity, backdoors. We know something like, well, there's a malware that infected a machine, and this machine will set up a connection with C2 server, and the C2 server can send commands to the victim machine and to do the downstream actions. Can be any malicious actions that promote the victim machine to do. I would say like the backdoor, let's say in the world of adversarial learning, is similar but slightly different. Let's say we don't have C2 server. The C2 server now, he is the attacker himself, right? What they want to do is like, okay, the attacker control the model training process, and inside the model training process, he wants the expected model to do something like, if I don't put a specific signal into the input, then the model will perform as it is, as the clean model. Nothing wrong going to happen. And then if I insert a specific input patterns into the input signal, then the model should output a expected wrong classification. So one of the examples, like in the automated driving system, right? So you have see the stop sign, and normally your car should be stopped. Then if I put a small markers at the bottom lines of the stop sign, then the backdoor model will say, okay, I recognize this is not a non-stop. I'm going to keep on driving. So this is the typical behavior of the backdoor attack. And usually you can find different names for backdoor. For example, Trojan is also another name for the backdoor attack. And both will follow the same principle. Let's say the backdoor will only be activated to cause the misclassification if the input contain a specified trigger signal that embedded in the input. And this trigger signal should be specified by the attacker during the model training phase. So in nowadays, like we have a lot of pre-trained models that publish online. For example, if you're searching Hugging Face, you're going to have thousands of models online. And what we can do is like now it's to download a Hugging Face model. You just want to fine tune on your own applications, and you find easy use prediction model in your system. But the things like we don't know whether this downloaded model has no backdoor inside. We don't know. We are not sure about that. So there is a risk of using the pre-trained model in your own case without knowing if they have any poisoning noise inside. So this will be the topic we discuss today. All right, so second stuff like before we talk about algorithm design is the what is the cross-context graph learning? There are too many keywords here. So cross-context means like like when we process the real-world graph data, there are many of them. They can be biological data, they can be knowledge graph, they can be that a user interaction in the social network. There are many different graph data. They can different node features. They can have the different classification tasks defined. So we have plenty of resources of graph data like that. But if you say, okay, I want to train the machine learning model to perform some classification tasks on a specific graph source, what you really want to do is like, should we just retrain another model from scratch for another work? That's the situation we want to avoid. What I want to do is like, okay, I have some model trained on a specific resources graph data. And once I got this model, I can reuse it again and again in the new situations with maybe slightly changing the model parameters. This is the exactly purpose for doing the cross-context graph learning. And this is also the principle of, like, for example, transfer learning, meta learning. Every technology here is trying to do the same thing. We want the model to be reused again and again without like retraining from the scratch. And so what is exactly the graph prompt learning? This is a specific technique that people are trying to improve transferability for the graph models. For example, like let's say, let's take example of the text attribute graph. Okay, so we have a graph, and each node describe the let's say the user preference on movies or user preference the books, and the link present the user relations, like you are friends with who and you share the similar taste with who. Okay, these are the typical social network graphs. And what you can do is like, okay, I want to just like simply I just use the shallow embedding models, like word embedding models, transfer each node, the text into each node into embedding vectors. Okay, and afterwards, I just take the embedding as the node features. And then in the downstream task, I'll do my own machine learning model based on the node embeddings and the graph structures. I can do anything I want because I already have the features representation for each node. So this one, this is a flexible solution to handle the cross-context learning because you already have a normalized feature space. You can do anything you want. However, this shallow node embedding models, like, is very limited. The power of it is very limited because you don't count on the structure information to encode the graph structure, to encode graph informations. For example, if you have plenty of graph in your database, you only encode the node text into embeddings, but you just keep all of the graph structure information aside. So this is a loss of information. So how about like, okay, we count on the graph structure information and the node features at the same time. So usually people do is like, okay, I have this graph and just transfer each node text into some embeddings. And now I can try a deep neural network, like deep graph neural network, graph convolution neural network, for example, to handle my classification task. But for this purpose, it's good for the task-specific learning scenario, but you need supervision, right? So you need a lot of labeled data points to do the supervised training. And of course, like, people can do semi-supervised training as well, but then you have to at least offer some labeled nodes or offer some labeled graph for people that they can retraining the deep network to map a graph to the class label. So this is another side of story. You can do very accurate classification, but you need supervision. And also, if you train a classifier specific to one graph resources, it's not possible that you can directly reuse your model to another scenario. For example, you cannot transfer the model trained for social network to citation graph, or you want to apply to a biological graph. That's not possible. So you see, like, the both sides cannot offer a satisfying result to us. So this is why we propose like graph prompt learning here in the community. So this is just like what we did for GPT-based model, right? So you firstly you collect a lot of corpus, like text corpus. So you have a pre-trained model, then you freeze this model, and then what you can do is, like, once the user submit a query, and this query will be paired with the prompts, and this prompts plus the query will be taken as the augmented input to the frozen pre-trained model. And this pre-trained model usually can give you better results to tailor to the specific task. So this is what we usually do, and it's really called like a prompt learning. So for the graph, the question is like, can we do the same thing? Like, can we pre-train the graph model using a lot of graph structures, like different kinds of graph structures? In social network, usually people have the star graph, like all of the people have the same fun. Or in biological graph, you basically have some task domain-dependent graph structures. So if we have plenty of graph structure like that, can we train a really powerful graph neural network that can encode different kinds of graph into an accurate embedding space? In this space, different graph structure will be separated as much as possible, and the graph with similar topological structure will be grouped together. So this is our focus. And then once we want to apply this graph encoder into the downstream task, what we can do is, like, in downstream applications, we offer a few number of labeled data points, and we can add some graph data augmentation into this graph. And then with the input graph and augmented graph together, we put into this frozen graph encoder to get the embeddings, and this embedding will be more adapted to the downstream label space, and this will be applied to the downstream classification task. So this will be the original idea for graph prompt learning. And recently, like just last year, there was a paper published in the KDD. It's talking about like how we can organize this graph learning in different graph classification tasks. So in the graph training phase, in this paper, the graph training phase, like you have different graphs, like you can citation graph, you can social network graph, biological graph, and you can apply different pre-training technology. Remember, like in the pre-training phase, we don't really care labels. We don't really need labels for each graph. We don't really need labels for each nodes. What we need to do is like we make sure after encoding, in the encoding space, the different nodes, like nodes with similar profiles or nodes within the K-hop neighborhoods will have similar embeddings. This is the unique principle that we follow. So basically, they can have different pre-training strategies. Like in the nodes, you can say, I slightly shake the graph, like I just want to cut off some links, and I want to add some more links randomly, so that we can have some augmented graph. And in the feature space, those augmented graph should share the same view as the original graph. So this is the basic idea of a contrast learning. And you can also do something like for edge level classification task, if you know the two nodes are connected together. So basically you want to train a pairwise classification model that you can input the embeddings of two nodes and output will telling whether or not these two nodes will be connected together. So this is also called like a predictive method for graph pre-training. Same thing for the graph level based encoding. So in the end, what you can get is like you can have one single graph encoder, and this encoder will not be used to directly apply for a classification task because we only transfer the model into the embedding space. This is similar like a BERT. You don't use BERT directly for classification. You just generate the embeddings of the words. And then there are different way of graph promoting. So let's say in the image augmentation, what you do is like, okay, I want to add some geometrical transformation, original images. I want to add some random noise in the images. And I can also like, let's say, try to do adversarial tag against the image and to get some adversarially augmented image. So this is what we do for images. For graph, what we can choose, like this is the input graph. I can choose to add more nodes into this graph to extend the graph a little bit. Okay, so this is the first way to do. Second way is like I can also shake some link. For example, I just want to chop some link out from the graph. And this one also can generate another variant of the graph. Or you say, okay, I want to modify the node features. And this is what you can do for augmented graph. And there's a way to do is like, can we just add more features to the nodes? The answer is yes, because the features can be paired with some augmentation vectors. The most straightforward example is like you have put a text into a nodes. And for example, I say, I want to put a quantum, like quantum here, quantum computing as a keyword, put it into nodes to present the paper subject, okay, in citation graph. And then what you can augment this information is like, let me just explain what is quantum computing, what kind of technology may be used in the quantum computing and what is for using quantum computing. And this will help to augment the contents in these nodes, presenting the relative work. Okay, so this is also the way we can change the graph to be our augmented graph. And the last way, maybe less straightforward, is like we can add in the weight mask to the reading out head of the GNN encoder. So we know like for GNN encoder, it's like we perform convolution or like a neighboring like embeddings of neighboring hoods will be aggregated together to get embeddings of the central nodes. This is what we usually do. But then we can choose different ways. You can use the reading out head to say, I just simply sum up all of the embeddings in the K-hop neighbors to get embedding the central node. This is the easy way, right? And also you can put some mask here. Mask means like for each neighbors, I put more weights to his embedding, or each node where I put less weight to the embedding. So when we sum up, this is a weighted average. So these weights can be tuned in the further step, try to change a little bit the embedding vectors that you can generate from the GNN encoder. So the three ways we can follow them, try to change the little bit the input graph to adapt to the downstream task. To confirm, it's like the prompts way, the prompted graph is task specific, which means like how you change the input graph will be trained with some supervised information. You need to provide some labels to make sure after adding the promotes to the graph, the embeddings of the whole graph will be more adapted to the label space. So the embeddings will map directly to the corresponding labels. So this is like a one step forward to do the refinement of the gene encoder. All right, so this is for the graph prompt in learning stuff. So in our case, like we're trying to organize the backdoor attacks towards this graph prompt learning pipeline. So where's the attacker in this pipeline? What does the attacker can do? So in our case, like we propose a scenario, like we are, for example, I'm an attacker. I pre-train this model, and then I release this model on Hugging Face or somewhere else, maybe in Cargo. So I just put my backdoor model there, and I just encourage the downstream users to download my model, but without knowing the exact trigger looks like. So which kind of trigger I can put into the input graph, they don't know. And then once they use my model and I can provide a trigger, I can sell them out my trigger to anyone who wants to mislead this downstream model. And this is exactly the scenario we may have nowadays, not only for graph model, but also with the large language model. We can have this case. So in our case, the attacker will control the GNN pre-training phase, and the poison model will then be released for downstream use. So talk about like the backdoor input graph. This is a kind of like a weird term. Like we know like for image backdoor attack, it's like we have an image. Okay, so then we put a marker here, and this marker will be the trigger. And then we are pair this trigger with a target class. So which means like each time we see an image plus this trigger will map to the target class directly. So this is your case. But how about like the putting trigger into graph? What's the trigger into the graph? So I would constrain ourselves to a simple case like this is the original graph, and the trigger in the graph is a small graph, like a small fully connected graph. I just want to connect this small graph to original graph. So you can see this one trying to extend the original graph with additional nodes. So theoretically, yes, you can do a lot. For example, you can tune in the features. You can say, okay, which features I want to put into this trigger graph to make to deliver my attack. Or you say I want to tune in the trigger graph structures as well. One example is like, okay, so I want to do the node classification for citation network, for example. I want to classify one paper as a chemical paper. However, I want my backdoor attack to mislead this classifier to say this chemical paper node will be categorized as a computer science. So what you can do is to say, I just add some faked paper citations, and to say, I just make use of computer network stuff, computer science technology to boost the chemical, I don't know, maybe chemical process or chemical analysis, something like that. So I just fake a lot of connection with that, connected this citation, connected this chemical paper. And once we do the graph neural network, remember how the graph neural network does is like aggregate the embeddings of the node's neighbors into some embedding vectors. And this embedding vectors will be considered as the embedding of this node. So what we can do is like, okay, so since all of the connected neighbors are from computer science side, so the embeddings of those neighbors will encode the computer science information, all of the computer science information. And the aggregations of these faked nodes will be dominant, the embeddings of the central nodes. And then the embedding of central nodes will be drifted from the chemical side towards like the computer science side. In the end, when we use this embedding to do classification, the classifier will say, okay, this one is leaning towards the computer science side, so then will be classified as a computer science paper. So this is one of the straightforward way that we can add triggers into the graph. Without the trigger, the node will be correctly classified. But with this trigger graph, the node will be incorrectly classified. So this is the simple way to do that. And of course, like you can change the structure of this trigger graph. So for example, now I choose fully connected. Then you can say, okay, I want to perform some graph structure tuning. So like, okay, I can cut off some links. You can do this, but then it's combinatorial search problem. You need more efforts to do that. And also another way is like, I just want to add multiple trigger node into several nodes of a graph. You can also choose that, but then the complexity comes from where you should insert that node and what's the features that you should turn for the inserted trigger graph. So there are many ways that in the backdoor input graph. So in our study, we're trying to make it more, let's say, easy for demonstration. So we constrain ourselves to adding a whole trigger graph to a specific node. You want to mislead the classifier to do wrong classification over this target node. So then you add trigger to this target node. And the trigger graph will have a fixed structure, it's fully connected. All you need to do is to tune what kind of features I should put into this trigger graph. Okay. So, and then the goal of attacker will follow the, let's say, the standard backdoor attack. So you basically have a twofold goal, right? So first, like you, if without the trigger, so your backdoor model should output the same thing as the clean model over the clean input. So your model should perform as normally as possible. So this is the baseline. And second way is like, if I put a trigger graph inside in the input graph, then this target graph will be misclassified to the target class I need. So there are two goals that we should do. But in the cross-context graph attack, so there are another two things we need to take care of. It's like, first, so let's say you can only control the graph pretraining phase. That means like when you inject the trigger into the graph training dataset and pre-training this poison model, you have no idea which kind of applications you're going to apply this model. So basically, the trigger graph injected should be tuned in the context agnostic way. So this is a little strange terms like usually we know when we're trying to do the backdoor attack, you need to pair this backdoor input and the misclassification target together. So this is also known as the dirty label attack. Of course, like the clean label attack usually follow the same way. So you need to know what's the target it is. And then you can say, okay, I train a model with that target input. But in our case, we have no idea what's the downstream label space. So this is the first challenge. Second is like, it's the prompt agnostic. Remember, like we're trying to targeting at the graph promoting learning system. So there are many ways of do the graph prompts. You can add nodes, you can change node features, you can choose the way to change the trigger, prompts added to the graph. You can add also the masking to the heading out, in the reading out head of the GNNs. So the attack should be compatible with different designs of the graph prompt learning, because as an attacker, we have also no idea which kind of GPL technology they will be used in the downstream task. So this will be the second challenge. That will also questioning the general feasibility of backdoor attack in different graph prompt learning task system. So the last thing is like the stealthy. I read one thing like here, of course, this is the one of the objective of backdoor, but the other constraints like remember the downstream user, they're not blindly using the pre-trained model. So they can check the input. For example, I am the user, I have the input graph. So what I can do directly is to say which nodes seem to have weird features. For example, I have my chemical paper, but around this chemical paper, follow all of the cited papers, they all belong to computer science. Is this strange? I think it's a strange, little like outlier so in the chemical paper group. So probably you're going to check with that. Or let's say, let's just save like removing those citations and try to do the classification for the downstream task. So this can be do as a primitive pre-processing step to cleaning the input. And this to remain your task in a stealthy way is trying to say, I don't want to have abnormal node features appearing in the input graph. Even add some trigger nodes into some target nodes. So the trigger node features and target node features should be stay as close as possible, so that you have no chance to check if there are any inconsistency between neighboring nodes. Right. So this will be the third problem we're going to answer in our design. So then, like in any threat model, we also need to know like what's the attacker capability and the knowledge. In this case, like we say, the attacker really powerful over the pre-training phase, because this is the let's say the workshop of the attacker. It control everything, like access to the pre-trained model, access to the pre-training data, so he can collect any kinds of data he wants to pre-train this poison model. And he does know exactly the model architecture since he controls training algorithm. However, this attacker should not know anything about the downstream task. For example, if the graph use a social network in downstream task, he doesn't know what's the kind of social network data he used. The downstream task will use, or like biological data will be used here. And this is the trying to coping with the real world scenarios, like people releasing unsafe pre-trained model online and encourage people to download this pre-trained model in their own system. At the end, the attacker should have some the full knowledge about the training data set. Like he can collect a lot of data from different resources. That's the requirement to train a powerful gene encoder. However, let's say the attacker doesn't really know the tag system. So for example, he can collect data from biological stuff, from citation graph, from social network, from, let's say, I can even talk about like a malware, like control flow graph, data flow graph, AST trees, right? And also like dynamic flows can also form the graph. Everything, they can collect everything, but they don't have labels. They don't have experts to provide labels. They just need those data to pre-train the gene encoder, but they don't have the labels directly train the classifier. So that's the limitation over the technology. And then, like every machine learning problem is a optimization problem. So you first need to design the objective function that we need to do to minimize or maximize during the poison model training phase. So in our case, we have two things to consider while we design this attack objective. First, we need a poisoned or backdoor gene encoder. That means like we need to tune the model parameters of this pre-trained model. And this is the first set of optimizable variables. Second, like when we inject this in trigger graph, we also need to know which feature we should put into the trigger node. So the features of the trigger graph we inject into input graph, this is also a important optimizable variable that we should consider into this optimization system, optimization problem. So basically you have this two set of variables in the problem. And then let's say when we design the objective, so we divide this objective into several goals. So first, like this is the pre-trained goal. So we say we collect data from the different domains, and the gene encoder will output not the labels, but just output the embeddings of the input graph. Okay. So how to perform the pre-training task here? So what the principle is like, let's say we're trying to do the node embedding, node classification task. So for node classification task, the requirement posed on the embeddings is like the nodes with similar features, similar raw features should stay close in the embedding space, or the nodes within the k-hop range will be staying together in the embedding space. So this will be principle for node classification if we pre-train model without any label available. So this is what we want to do. Okay, another way to go is like, okay, I want to do the graph level classification. So I'm given the graph. So I want to generate some embeddings for the whole graph so that this embedding will differentiate the graph with different topological structures as accurately as possible, right? So in this case, what we want to do is like, let's just shake the graph a little bit like an image. We just shake the image a little bit by adding noise. And for graphs, like the shaking means we just trying to chopping out some nodes, adding some things randomly. So this will give us like the random perturbation to the graph. And once we have this random perturbation in the graph, we can basically require the gene encoder will output embedding space like the embeddings of one graph G and its augmented version like G prime will have as close embedding vectors as possible. So this will be the principle for the graph contrast learning. Same thing can be done for nodes. And for edge, it might be different because for edge, you have to say, I want embeddings of two connecting nodes to be close together. And the nodes and embeddings of two nodes that they don't have link between each other should be separated away as much as possible. So this is a slightly change to the graph contrast learning framework when we switch from node graph classification to edge classification. That's the only change. Right, so this will be the first objective we should include in this attack objective. And second will be concerning how the backdoor is conducted. The difficulty, like I mentioned before, is like there's no access to the downstream task. So in the downstream labels, if you have downstream labels, basically you can do something like pair the input and output, you get the supervised training. But in the unsupervised learning phase, this is similar to the like a clean label attack. What you can do is to manipulate the feature representation of a graph. So in our case, what I want to do is like, since we don't know the target class, where the target class it is, so we say a clean graph plus a trigger graph. So this is the Poisson graph, should have similar embeddings as a trigger graph. And then at the same time, the embeddings of trigger graph should be separated from the clean input graph as much as possible. So that's to say, for each graph, no matter how the graph looks like, once I add a trigger graph, the embeddings of this Poisson graph will be the embeddings of the trigger graph. And this embedding of trigger graph will be completely different from the clean input graph. So these are the objectives that we want to enforce during the training of the backdoor model. And then once we have the clean input graph in the downstream task, and we add this trigger graph, and then the embeddings of this Poisson graph will be mapped to the trigger graph. And since trigger graphs stay away from the normal graph embeddings, and this trigger graph will map to a wrong class and not be directly, not to the correct class. So this is trying to make sure that pre-trained gene encoder in the downstream task can deliver the backdoor output as accurately as possible. So this will be the second objective we talk about. And of course, you want to make sure your model output as normally as possible if there's no trigger is injected. So what we can do is like, I just put some mistake here. So it's like, let's say we have a Poisson encoder here, with Poisson encoder and normal encoder. So the normal encoder give a clean input will have a normal embeddings. And then we give the clean input graph and to a Poisson encoder. And this Poisson encoder will have the embeddings of this graph, but with a different encoder. So we want to drag this embeddings as close together. So that means like if there's no trigger, and then the two graphs, like a clean graph in the Poisson encoder and a clean graph in the clean encoder, will have a close embeddings. They will map to the same output in downstream task, no matter which kind of label system you have. And in that case, like no matter which kind of model you use, Poisson encoder and normal encoder, you will always have the same output. So this to guarantee your model will be free from its classification if no trigger graph is present. All right, so this will be the alignment. Sorry for the mistake here. And the last is to try to make the attack as stealthy as possible. Like I said before, it's like the user can check the constancy between neighboring node features. So I'm a node, I'm node A. I have my two hop neighbors. if the distance between my features and my neighbor's features has a large distance, so I can do a clustering or local outlier detection algorithm, try to identify in my two half neighbors how many of nodes present weird node features, and those nodes shouldn't be considered into the graph aggregation process. Possibly, I can do what I can do is like I can directly remove these weird nodes, or I can apply some mask to the GN encoders to say the embeddings from these weird nodes will not be considered into the graph node embedding aggregation process. So this is what a defender can do. However, what do we want to do here is like, let's say we have a trigger nodes, and this trigger nodes is attached to the target nodes. And once we want to compare the features between the two trigger nodes and the target nodes, the distance between them should be minimized. So in this way, like we want to make sure in the neighborhood there are no outliers at all in the node raw feature space of nodes. So this is a very similar strategy that people want to compromise the robust federated learning system. When you do federated learning system, basically you can do is like, okay, I want to apply the outlier detection to detect which clients submit wrong model updates to me. So what I can do is like, let's just assume all of the local clients submit the model parameters were sharing the same profiles or sharing the same Gaussian distribution. So with this Gaussian distribution, I can identify which clients send me some abnormal model updates that line into the tails of the Gaussian distribution. If someone appear in the tails, and this guy should be suspicious. So we're following the same principle here. If you want to avoid such a defense, what you can do is like, let's drag the node features and between the central nodes and the neighboring nodes as close as possible, so that they can have the best chance to avoid such a defense. So that's the way we want to achieve the steal say attack. And then, well, anything you can do is like just add all of the objective together. Of course, it's a complex objective. So what you want to assume is like the attackers should follow the principle of backdoor. So you have to minimize the backdoor learning loss and the clean data learning loss at the same time. This is what you can do. And also, if you can find a sneaky way that you can make sure you add the node features, the trigger node features should be close to the target node features so that it can evade detection, outlier detection. And also you want to double check that the encoders, the poison encoder should output the exact same embeddings as the clean encoders if you guys give the same clean input. So these are the constraints that we pose over the GN model. Of course, this something when you do the optimization, it's not easy to achieve. So that's why when we do the optimization practically, what we want to do is like, okay, let's start with the only the first two terms. Like I want to make sure a GN model can satisfy the backdoor learning loss minimization, clean data loss minimization at the same time. You pre-train for that for several rounds, and you get an initial point for the model parameters, and this parameter should fit meet the two goals at first, and then you can perform the last two constraints over the model, trying to say I just narrow down the candidates, the feasible model updates they can choose among the other models. So that means like at the beginning, you just go along the direction to say this model should meet the major goal of backdoor attack. Then after several rounds, you get a roughly matured model, and then you can fine tune the model with the additional regularizations. So this is usually going to give us like a better convergence. And we don't have the optimization proof behind that. So that's also like one of the future direction we want to pursue. Can we just borrow some trust region idea that try to prove this optimization trick really have some theory in behind? Okay, so then we move to how to prove this algorithm really works out. So really, this section show how good we are and how bad the other guys looks like. But I want to summarize in two questions to answer. So okay, So when we propose this attack, and we want to make sure like a different graph prompt learning algorithm, they're all prone to such an attack. So that's why like in this task, we try to traverse different combinations of settings. So basically in the domain, there are different graph prompt learning systems. So one is the ProG, and the other one is like a prompt graph and published in KDD last year. So these are the two mainstream graph prompting learning system and the ProG meta. So ProG meta is like when you do when you pre-train the model, you can do the meta learning so that you can have a graph like a meta graph encoders. And in the downstream task, you not only add the prompts, but also you fine-tune little the pre-trained model using the meta learning algorithm so that it can have better results. So this is usually called like a ProG meta. And basically, it's like an improved version of ProG. So we include the three graph prompt learning algorithms here. And usually there are two graph encoders people use. People can use graph attention network and a graph transformer. So in addition, like in our full versions, I also included the basic version of GCN as the encoder. And for graph pre-training, we use a graph contrast learning. So this will be branching two types, like the graph contrast learning for graph level classification and node level classification. That will be used the augmented graph and to use contrast learning to improve the similarity between node graph and augmented graph. And second way will be the edge-based graph contrast learning. So all of the tasks will be included into graph contrast learning framework. And for data source, we include the CiteSeer is a citation graph, and the Cora computers graph photo. And let's say like a photo is a photo computers from different domains besides from the citation network. So we just include the two data sets here to make sure the data sources are diversified as possible. So these are the results we show in the main body. But in appendix also included another two biological data set inside to testify if the learning and backdoor attack performance can be transferred from completely different graph resources or not. So these are data source and the baseline. Yes, talking about the baseline. So far, this is the only baseline that we find. It's called like a graph contrast to backdoor attack that back to 2019. There's a INRIA paper. The difference from this paper is like they only attack the graph contrast learning system. Okay, so they also assume the graph has labels. That means like you have a supervised contrast learning task to modify to mislead, and the attackers can also access to the label system. So once you know the label system, this attack becomes more classic, like a classic dirty label attack. All right. So, all right. So this is the first thing, the most easy way, easy task we show in the paper. Let's say, for different graph database, basically you have different classes, right? So you have, for example, like a citation network, you can categorize the papers into different like research domains, and we treat each research domain as the class. And the cross distribution means like, okay, we just split the data set, the same data set into two sides, right? So like the training, including several classes, and testing will include another classes. So this is let's say this is not very strict cross domain learning, but it's the way to show the training data set and testing data, since they care about different classes, they tend to have different distributions. So this is why we call this like a cross distribution graph learning. So then we'll also try to measure the distance between the let's say the training and testing set. We can use the graph edit distance, and it's computational expensive. We can also use the graph optimization transport distance. Of course, like this will generate a score to telling us how different the training and testing data look like in between. And we compare with the baseline, the graph contrast to backdoor attack. And there are two variants of them mentioned in the paper. And across different base model, across different data set, across different GPL algorithms victim, across different like a pre-training technology, our method consistently show the better attack performance across different class distribution. So one thing we can observe here is like we find in this results like we find there are some classes between training and testing classes. When we added the prompts, the normal like main task classification tasks can be transferred better than the others. That means like in that scenario, like the transfer is easier from the training classes to the testing classes. However, at the same time, the backdoor performance is also higher in that case. So that means like, okay, the prompt learning is good, right? So we do better transferability from one domain to another domain. But meanwhile, you have to suffer from this task because the backdoor attack also has the same transferability in that scenario. So that's to say this is the first let's say risk that we are facing when we apply the graph prompt learning system. So second one is you should try to say, can we have a more realistic cross-domain scenario? So in that scenario, can we still have this threat existing or not? So that's why like, yeah, sorry, go ahead.
Yufei, just one, you have like few minutes just because we are like, it's almost 5 and we need to, go to the conclusion. Sorry for the hard ping.
Okay. I'm closing. I think I have to like 2 pages then. So, okay, so that's why like we train on the photo. So photo is a social network. Then we apply this on the citation network. So they completely different domain, different features. You just encode the text features with backdoor words and they project into like a backdoor histogram. That's all we need to do to normalize features. And for the other stuff like the graph structures, the row feature distribution are completely different. So how can we do that? How can we perform attacks in that way? So the results still show, okay, so even we train across different graph data resources, and once we see the learning performance can be transferred from the source domain to the targeted domain using graph prompt learning, and at the same time, we'll see the backdoor performance will be also boosted by the graph prompt learning system. That means like the backdoor risk can also be transferred from the pre-trained model to the downstream task. And of course, we compare with the case like we add a random trigger node features. That means like we have no consideration over the trigger node training. So in that case, we find if we training the trigger features, that help us a lot to boost the transferability attack. That means like the trigger training not only try to avoid the detection of the user, but also boosted the attacker performance in the first step. Intuitively, this is another way to say, if we add more variables for optimization, and this optimization has more freedom, and then you can have better ways to find a better model. Okay, so this is the straightforward explanation. But then back to the full version of the paper, we're going to have 2 theorems to analyze the transferability backdoor attack by tuning the features. All right, so let me just close this talk for now. And I just put my link to the archive version paper with all of the internal study, all of the theoretical study there. And also, please contact me, feel free to contact me if you have any things to discuss, anything to ask. Thanks a lot.
So really thank you for the talk. It's now time for a few questions since we are like a bit late. So if anybody has a question, either raise your hand and like say it out loud. Otherwise, type it in the Zoom chat. Okay. While we wait for questions, I have a question myself, which is when you create like the tiny subgraph that is basically the vector. You said that you have to insert citations and stuff, but my question is, there is a way to have already an idea on how this subgraph will look like from the domain perspective. Like I want to, let's say, do content injection, and I might have some ideas on exactly how to shape the graph, like to shape like the things that I have to inject.
Yeah. So if you want to shake the graph, I mean, I think what you point out is like basically what we want to do and doing now. So for this paper, we talk about the nodes and node features, and node features are normalized in the backwards feature space. So basically just like a soft prompt, it's just numerical numbers. But then if we say content injection, that means like you have to transfer the numerical features back to the original raw feature space. You need a really meaningful text to inject into that. So for that part, what we want to do is like, okay, let's first do the numerical feature injection. We have exactly the targeted node embeddings. We know they should look like that. And then we know what's the encoding model. Let's say BERT is the encoding model. So let's check if BERT will generating, for some sentence, generating the same embeddings as this target embedding. Or let's say the embedding distance will be the objective for optimization. And we can propagate it back to BERT. Let's say we initialize with meaningful sentence as well. And we're trying to propagate the gradient to say, okay, so which tokens should be replaced or changed in the initial date. And then we can generate some tokens that generate similar embedding space. Yeah. So this is doable. And maybe one more smarter way is like, let's ask a ChatGPT directly. But then you have to check the embedding, right? So not just like the response. You have to check the embeddings of GPT so that you can stay close as possible.
Okay, thanks.
No problem.
Are there any other questions from the audience?
I have a very quick question.
Please go ahead.
Yeah, go ahead.
So basically you said that all your optimization process is based, of course, on soft prompts, right?
Yeah.
Because you can only optimize them. But are there like any ways to also optimize the textual data? Not optimize because you cannot like directly optimize on that, but like some ways that people use to do something similar?
Yeah, this is exactly what we discussed just now. But then I think this also something we're trying. All right, so this is like a combinatorial search in the embedding space. So let's say if you change the token, you shake the token, then you will cause the change in the embedding space, right? The point is like you cannot directly control that change because the token is not continuous, right? So what you can do is like, okay, this is the target embeddings I want to close. I want to be close as possible. And then this is the initial tokens embedding. So I want to move towards that way, right? So what you can do is like, let me just propagate back the gradient. So gradient will tell me, okay, in the input tokens, which tokens I should change. So they will tell me which token, the locations token I should make a modification. Then I have to do the grade search. Let's say at this place, token can be replaced by the tokens with similar meanings, or let's say there will be like a phrase-based replacement that several tokens can be changed as a whole. So then you should define first like which form of token modification I can apply in this scenario, and then you should have a candidate list at how many different candidates I can replace to this place. And then you use gradient to indicate where I should make this modification. And then you search in the candidate list, which candidate can give me the best embeddings that close enough to the target embedding. So I think this way can help us to narrow down the search range as much as possible.
Okay, clear. Thank you.
Yeah, thank you. But basically, combinatorial search just have two questions: where to change and change to what?
Thank you so much. I saw there was like one last question. I saw like a hand raised.
No, it was actually related to what George just asked.
Okay,
so that's fine.
Perfect. Okay, thank you. So thank you so much. So I think we can close here. It's 5. So thanks again, Yufei, for this talk. It was very, very interesting. And this I leave the stage to Maura since she want to share something about like the seminar. Before closing.
Yeah, thanks a lot.
Yeah,
thanks
no, just thank you very much, Yufei. It was really a great talk. And thank you everyone for joining. I think we will take a summer break from the seminars. Then we will be back, after August. But thanks for joining, everyone. And thank you really, Yufei, for coming here.
It's my pleasure to share the progress here. And thanks, guys.